Hello, my dear friends. Welcome to this discussion. We are discussing in details the solution to the partial differential equation as defined by Laplace. So, the Laplace equation is a very fundamental partial differential equation that is usually met in physics, engineering, and applied mathematics. The Laplace equation appears in many steady-state problems where there is no change over time. And a summary of a number of applications has been given in one of our earlier discussions, and you can find the link in the description of this lecture. But to just highlight, we find it in electrostatics and magnetostatics, in fluid dynamics, to study the rotational flow in aerodynamics and hydrodynamics, in heat conduction, to study the steady state temperature distribution, in gravitational fields, to model planetary gravity, and in image processing, for example, in MRI and CT scans, to enhance them so that we have edge detection and deblurring the images. Then we also look at it in quantum mechanics and quantum physics, in free particle wave functions, and later on in structural engineering for stress analysis in materials. So what we are going to do, we are going to write our partial differential equation. So we have the Laplace equation given by del 2 del 2u del x squared plus del 2u del y squared equivalent to 0, and this is in 2 dimensions. So if this side is not equal to 0, so if the right hand side is not equal to 0, this becomes the Poisson equation. So Poisson equation and Laplace are very much related, because if you don't have a function here and if the function here is equal to 0, then we shall call it the Laplace equation. If the function is not equal to 0, we call it the Poisson equation. Then in 3 dimension, we'll have now the x, y, z. So we have del 2u del x squared plus del 2u del y squared plus del 2u then del z squared is equal to 0. This is also Laplace equation in three dimensions. So now, to begin with, we want to look at electric potential distribution or temperature distribution over a plane area that has been subject to a number of boundary conditions. We find that that phenomena can be described by the Laplace equation. Now, if we consider the potential at a point P, if this is our point P that we are talking about, okay, in a plane, then you find that if it is indicated by the ordinate axis, it will be a function of its position. You'll find this is Z or Z, this is Y, this is X, and therefore if it is a function, if we find that the potential at a point P in this plane, it will be the function of its position. So you'll find that Z is equal to a function of X, Y. So this becomes a solution to the to the partial differential equation, this del 2u del x squared that we are calling the Laplace equation. Now, if we consider this being now the solution, if we are talking about this being the solution to the ordinary differential equation, you are likely to have something like this on this surface. So if this is O, you have P, you have Q, you have R here, and then this is X, this is Y, this can be a solution to the partial differential equation that we are calling the Laplace equation in 2 dimensions. And then if we talk about this and this being the solution, we will find ourselves stating a number of boundary conditions. So the boundary conditions that we consider here include u equivalent to 0 when x is equal to 0, and that means, that is to say, u of 0, y is equal to 0 for values of 0 less y less b. Also, this is 1. Now, number 2 is that u can also equal to 0. That is if we have x is equal to a. So that is to say u of a, y, is equivalent to 0 for 0 less than y less or equal to b. Then the third boundary condition that we always consider is u is equal to 0 when y is equal to b. And that is to say u of x, then b is equal to 0 for 0 less or equal to x less or equal to a. Then the fourth boundary condition is that u is equal to 0 when you have y equivalent or equal to 0. So that is to say u of x, then 0, this is equal to 0 for values of x between 0 and a. So for 0 less x or equal to a. So once we have our boundary conditions, we can now take an assumption. So let's assume, we are going to assume the solution of the PDE, that is the Laplace equation, to be u. We have earlier on said that it is a function of x and y, and this is going to be x of x times y of y. So if we take an assumption that since this solution is going to be dependent on the position or the value of x and y, then we can say it is going to be a function that is composed of two functions, one which is x as a function of x and another one as y being a function of y, being multiplied together. So simplifying this, we can say this is u is equal to x, y. So now, having u equivalent to x, y, we can start differentiating. So partially differentiating. So partially differentiating this gives what? So del x, for example, this is going to be x prime, then y, and then del u. So if we again differentiate this partially with respect to x, that is d by dx of del u del x, this gives us x double prime and y. So what about when we consider the y side differentiating or partially differentiating this function with respect to y? That means I'll keep x a constant and then I vary y. So this becomes del u del y, and this is going to be x, y, single prime. And then if we take a second partial derivative, this becomes del 2 del y squared is equal to xy double prime. So if we can consider this to be maybe equation 2, then we consider the partial differential equation to be the equation 1. So if it becomes equation 1, I'm going to substitute. So I'm going to put equation 2 in 1. So if I put in 1, remember, these are now derivatives, so I'm just going to substitute, and I'll have, in place of del 2 u del x squared, I'll have x double prime, then y plus x y double prime, and this is equal to 0. So I'm going to do what we call separation of variables. So separation of variables, and this is going to give us what? This is going to give us x double prime, y is equal to negative x, y double prime. So if I separate the variables, then still this is going to give me x double prime divided by x equivalent to y double prime divided by y, but this becomes a negative. So once I'm here, I can say let x double prime out of x equivalent to negative y double prime out of y equivalent to lambda. Let us equate this to lambda because if x is a function of x only and y being a function of y only, then if we have such a kind of scenario, then this is going to be a constant, and it is very correct. So we can take that assumption that let this equivalent to a constant. So let that lambda itself be equivalent to negative, for example, p squared. We are taking a case where lambda is greater than 0. You can try for the cases of lambda equal to 0 and lambda greater than 0, but these two cases are going to be useless in our discussion in a way that they will consume much of our time. So you can try it in your own time, and you'll find that they will give no oscillatory solutions. So since they give no oscillatory solutions, we are going to discard them and then go with that part where lambda is less than 0, because it is what is going to give us oscillatory solution, and that will be the desirable one. Therefore, if x double prime divided by x is equal to negative y double prime divided by y is equal to negative p squared, then we are going to formulate ordinary differential equations here. So from which x double prime minus is equal to negative p squared times x, and this gives us x double prime plus p squared x. Then the other one is what? The other one is going to be y double prime is equal to negative p squared. Remember, this was negative, so it becomes negative p squared y, so that the negative cancels, and so what is going to happen is that this and this is going to go, so that we have y double prime minus p squared y is equal to 0. So if we equate also this to 0, we'll find that maybe this is equation 3. So solving 3 using methods of solving ordinary differential equations, you'll find that if we now use the D operator, we are going to create the auxiliary equation, which auxiliary equation for the case of x squared minus this is going to be plus p squared x, so we'll form m squared plus p squared is equal to 0, which would give us m is equal to plus o minus jp. And then for the other side, it will be m squared minus p squared is equal to 0, from which m becomes plus o minus p. So meaning, what solutions are we going to get? I will have x equivalent to a cos. Where does that come from? Let me just put it here so that maybe we later on do that. So this is going to be a. Let me use maybe a small a. Let me use a small. Let me use which other constant haven't we used? Let me use alpha. Okay, alpha exponential of px plus beta exponential of negative px. Remember, this is j, and you have a j here. So these ones will form, if we now remember that ej, for example, px is equal to cos cosine of px plus sine px. Then this will become cosine of px plus actually I. Here we have not put I, but I should be on sine. Then this I or j, we are going to take a minus. So the whole of this now becomes a cos px plus b sine px. So that is the solution for x. And then for the y side, for this y, we are going to find that this is going to be what? So this y is going to be c exponential of py plus d exponential of negative py. C and d are just arbitrary constants, and so we are just not getting them from anywhere, but they are just arbitrary constants. So let's continue and proceed. So this is d exponential negative py. So when we combine, we will find that u equivalent to x, y will be x, which is a cos px plus b sine px, and then we are multiplying this by ce exponential py plus d exponential negative py. So this is the general solution. Now we can do a little more manipulation of y, this y equivalent to c exponential of py plus d exponential of negative py by taking by putting it into hyperbolic functions. So we know that epy, for example, plus e negative py, everything out of 2 is equal to cos py. Then we also know that a half, okay, a half exponential py minus exponential negative py is equal to sine is going to be a sine. Yes, it's going to be sine, or the hyperbolic sine py. So if I add, this is I, this is 2. If I add I and 2, I'll find that I will have what? I will have e py equivalent to is going to be equivalent to is going to be cos or hyperbolic cosine py plus hyperbolic sine py. Then negative exponential py will be from subtracting 1. We are going to subtract 2 from 1. So I'm going to get subtract I and 2. So if I subtract I and 2, I'll get exponential of negative py, which is equivalent to what? Which is equivalent to the hyperbolic cosine py minus hyperbolic sine or sine py. So if I now introduce in my constants, that is c and d, then y itself becomes, I'm going to have c, then I'll have hyperbolic cosine py plus sine, hyperbolic sine py, okay? Then we are adding hyperbolic, that is d times hyperbolic cosine py and minus hyperbolic sine py. So if I reorganize this, I'll have c plus d times cos py plus c minus d sine py. And remember, this is still our y. So what does this call us to do? This is still a constant, and this is also a constant. So I can say this is c prime and cos py plus d prime sine py. So that is y. And then what I'm going to do, I'm going to use a phase shifted hyperbolic sine function to summarize this. So using a phase shifted hyperbolic sine function, we shall have another form. So the other form, another form for y is e, then hyperbolic sine p, then y plus the phase shift. So the phase shift is phi that we are using, and therefore meaning our y will become e, which is now another constant that we have introduced in, then shine p into y plus phi. So what becomes of our solution? Our solution, which is u, a function of x and y, becomes a cos px plus b sine px. Then we are multiplying this by e sine p y plus phi. So we can now multiply this e throughout so that we are able to determine other or reduce on the number of constants. So u x y is equal to p cos px plus 2 sine px times sine, or the hyperbolic sine function of p of y plus phi. So whereby AE is equal to capital P, and BE is going to be the Q. Yes. So what next? We are now going to apply the boundary conditions. So now applying the boundary conditions, So the first boundary condition, remember we said that number one, u is equal to 0 when x is equal to 0. So we say the u 0 of y will become 0. That is for 0 less y less what? Less b. So what does that call us to do? We are going to substitute x is equal to 0 here. So u 0y, which is equal to 0, will be p plus. Because the sign of 0 is a 0, so we shall have a 0. Then, okay, then we add or we multiply this shine p y plus phi. So what is this equivalent to? This is going to be p shine, that is p y plus phi, and this is equal to 0. So what does this mean? We know if this is to hold for all values of y, so for all values of y, then p can equal to 0, but shine p y plus phi will never equal to 0 if this is to hold. So that means it leaves us with a solution of u x y equivalent to p. P is equal to 0, so we shall have 2 sine px, and then we put the hyperbolic sine function h, then p y plus phi. Okay, so the second boundary condition, we know that u is equal to 0 when x is equal to a. So that means we are going to put u a0, ay equal to 0. So if we put a 0 here, what will this become? This is going to be 0 is equivalent to 2 sine p a of hyperbolic sine p y plus phi. So what does this tell us? We said this, if this is to hold for all values of y, 0 less y less b. Okay? So for all values of y in this range, Then 2, first of all, can't be 0. Sine p y, I mean the hyperbolic function of p of y and phi cannot also equal to 0. So this leaves us with the only choice of saying sine PA can equal to 0. So this is true if PA is equal to n pi. So giving us the value of P as n pi out of what? Out of A. So for that matter, therefore, what we can do is that we can go back and substitute in uxy is equal to 2 sine px shine py plus phi, okay? And we are saying this is going to be our solution for now. So let's substitute in another boundary condition. So why are we doing this? We are just going to substitute in our n pi out of A later on, but let's keep P to make our equation simplified. So the third boundary condition that we are going to put, we know that u is equal to 0 when y is equal to b. That is another boundary condition that we are going to be putting. So meaning uxb is equal to 0. So we're going to substitute where there is y, we are going to put b there, so that we have 0 equivalent to sine px hyperbolic sine p of what? This is y, which is going to be b plus phi, and this is equal to 0 as we have said. So if this is to be true, to hold for all values of x, then 2 cannot equal to 0, sine px cannot equal to 0, but it leaves us with an option of saying the hyperbolic sine p b plus 2 is equal to 0. So if this is to happen, then we know that always if a sine of anything is going to be 0, then that angle itself can be 0. So meaning b plus phi is equal to 0, giving us the fact that phi is going to be negative b. So if we rewrite our solution, this is going to be uxy is equal to 2 sine px, then the hyperbolic sine function p, then we have, remember we had y in here, so and phi. So where there is phi, we put negative b, so we'll have y minus p. So, but you recall the fact that for odd functions, for example, a sine of negative z is the same as negative sine z. So if I use the same simplification, I can come and say uxy is equal to negative 2, then sine px, then the hyperbolic sine p of what? Of b minus y. So this is the same as what is here. And then if we further simplify this, this becomes uxy. This is going to be 2 sine px, then sine p of b minus y for 2 is equal to negative 2. They are all constants, so I can replace it with another constant to 1. So now if we recall that p is equal to n pi out of a, for n is equal to 1, 2, 3, up to infinity, there are going to be a number of values of uxy. So if that is the case, then we shall have a general expression unxy equivalent to summation from n is equal to 1 up to infinity of 2n. We just convert this 2 1 to 2n, because for each and every value of n, we are going to be having a different expression whereby even 2 is going to be inclusive, or is going to be of a different expression. So this is going to be 2n sine n pi x out of a. Then we'll have the hyperbolic sine pi n out of a, then times b minus y. So let's apply the fourth boundary condition. And the fourth boundary condition, you know that u of x0, okay, is equal to a function of x. That is when y is equal to 0. Obviously, for the range of values of 0, less x, less what, less a. This is supposed to be a. So now, what does that tell us? We can get now f of x. So f of x is going to be the sum, okay, of from n is equal to 1 up to infinity of 2n sine n pi x out of a. If we substitute y is equal to 0 here in this expression, we shall have hyperbolic sine pi n out of a times b. So we'll have the hyperbolic function of sine n pi out of a, then we'll have b. What does this mean? It tells us that the Fourier coefficient, therefore, the Fourier coefficient 2n, this is going to be actually 2n hyperbolic sine n pi b out of a. So I'm going to multiply by sine here as hyperbolic sine pi n out of a times b. This is going to be then times 2n is going to be twice times the mean value of f of x, then sine n pi x out of a. This is already established, but also when you look at this, you have that this is going to be f of x, and you have a sine of function, sine function n pi x out of a. So what you have as constants are going to be 2n and the hyperbolic sine of n pi b out of a. So meaning whatever you're going to call a Fourier coefficient is going to be 2n, then hyperbolic sine function n pi b out of a. So meaning, if we know that the mean value of f of x, okay, sine n pi x out of a, 2 out of a integrating from 0 to a, f of x sine n pi x out of a with respect to x, obviously. So that means I'm just going to substitute in here so that I will have, this is actually going to be 1. It is supposed to be 1 out of. It's supposed to be 1 out of. So I'm going to say that that 2n will therefore equal to 2 out of a times 1 out of a hyperbolic sine pi n out of a times b, integrating from 0 to a of f of x sine n pi x out of a with respect to x. So once I have this, I can just come again and substitute it in this expression for u, x, y, and then I'll have the function of u, x, y that will be a solution to the partial differential equation. Therefore, the solution becomes u, x, y, which will be now the summation, okay, for n is equal to 1 up to infinity of 2 out of a times 1 out of the hyperbolic sine function pi n b out of a. Then we are integrating from 0 to a fx or f of x, then n pi x out of a with respect to x. Then we are multiplying it by sine n pi x out of a, then times sine the hyperbolic sine function of b minus y. B minus y, remember you have a p here. So we have a p here. We had a p, but a p is equal to n pi, okay? This is n pi out of a into b minus y. So that is our expression that gives us the solution, solution to the Laplace partial differential equation. Thank you so much.